Now let us go through the code for the SysTick timer. Now as we know, the SysTick timer is a 24-bit down counter. So in this part of the segment, we are going to talk about the requirement. That is what we need the SysTick timer to do. So let us start with the assumption that we need to set the timer for a 250 milliseconds timeout. So 250 milliseconds would mean 0.25 seconds. Now, so we don't have an idea about which clock to use. That is, whether we should use the prescaler clock or whether you should use the main clock. Now, I say that because not all the counts that you are going to get. So the frequency that we are going to use for our board is 84 megahertz. Now, for 84 megahertz, if we set certain counts, for example, we may be getting a count, but we have to see whether it is going to fit into the 24-bit register, that is the reload register. Okay, so that is one check that we always need to do before we set up the SysTick timer. A mistake that is often made is, say you get a count which exceeds 24 bits and then you fill that value in the reload register without realizing that the top part of the higher bits are going to get truncated. So the behavior of the SysTick timer is faulty. So you have to be careful about that. So the SysTick timer will be counting down, of course, faster than you have planned it to. Let's do the calculation. So we know that the frequency here is 84 megahertz. So for an 84 megahertz frequency, what should the reload value be? Say for 0.25 seconds. So for 1 second, we saw that the count should be 84 into 10 to the power of 6. Of course, because this is following the clock cycle. So obviously, when so many clocks, that is when so many cycles expire, it is 1 second elapsed. So we know about that. So if we have to make it 0.25 seconds, the logic is we have to divide this count by 4. So this count has to be divided by 4, because 84 megahertz means 84 into 10 to the power of 6 cycles in 1 second. So if we keep those many cycles in the reload value register, if it were possible, it's not possible because the value is too big, and we allowed the processor to work at 84 megahertz. So the countdown, because this is operating at the frequency of the processor clock, it will need 84 into 10 to the power of 6 clock cycles for 1 second to elapse. Now, so for a quarter second, we will need 84 into 10 to the power of 6 divided by 4. That is that many clocks. So that value is going to be 21 into 10 to the power of 6. Now, let us open up the calculator and check if this value can be accommodated in the 24-bit register. So the way to do it is, open up your calculator. Let me erase this. So remember 21 into 10 to the power of 6. So let's erase this. And write 21 in decimal. Let's write 21,000,000. So this is 21 into 10 to the power of 6. And we know that for causing an interrupt, the count should be 1 less. So we have to do minus 1. So this is the value. Now we will have to then see whether this value is going to fit into the 24-bit register. So let's count. So 4, 8, 12, 16, 20, 24, 25. So do you see this? This value cannot fit into the 24-bit register because it is exceeding by 1 bit position. We have to keep the count confined between 24 bits. So this is what we need to confine it within. Now for us to have 0.25 seconds, then that is, we need to use the divide by 8 that we have here in the SysTick timer block. Okay, so if we use the divide by 8, what happens? So using the divide by 8 counter would mean that the SysTick timer is seeing a slower clock from the, so it sees a slower clock. So it sees a slower clock. So that means the system clock is 84 megahertz or 84 into 10 to the power of 6 hertz. If you divide this by 8, okay, so 84 into 10 to the power of 6 divided by 8, let us open up the calculator. What do we see? So let's do 84,000,000, that is 84 into 10 to the power of 6, and let's divide this by 8. We get this value 105,000,000. Let's do a -1 because that is what the actual count should be, and the count is A0379F. Okay. Now let's see if, so this is for 1 second. Okay, our target is 0.25 seconds. So let's see if 1 second is possible here. So it is 1, 1, 1, 1. So 4, 8, 12, 16, 20, 24. So as you can see, 1 second clock is also, 1 second timeout is also possible. But in our case, our target is 0.25 seconds. So 0.25 seconds would mean we have to divide this count further by 4. So let's do that. So 105,000,000, okay, and then we divide this by 4. So the final value that we are getting is 2625000, which is this value 280DE8, that is the hex value. So if we subtract 1 from this hex value, the value that we are getting is 2D80DE7, and of course this value will fit into the 24-bit reload register. So 4, 8, 12, 16, 20, so it's just 22 bits. So we have to have this value in the reload value register for the timeout to be 0.25 seconds. So we needed to use the prescaler, that is we needed to use the divide by 8 block because if we had used the system clock directly, we would not get the timeout as we desire. And for slower clocks, for slower timeouts, we have to use the divide by 8 block. So we have to write the code to reflect this. So if we go into the code now, we have so let us just write down the value here. So I've already kept the value written 280DE7. So this is the value, this is the hex value that we have written. So when we go through the code next, we will explain the enable SysTick function and all the registers and all the values that we are working on. Now let's start from the beginning. Let's start from say we don't have the SysTick interrupt right now in the code. Just let's pretend that we don't have the SysTick interrupt in the code. We have to include the SysTick interrupt. That's the first thing we have to do. Is to go into the startup file. Now before we go into the startup file, here we have to check the programmer's manual. Okay, so it is here right now, but then imagine that if you had got a startup file with all default handlers here, SysTick handler was not here, and even this one exti0 handler was not here. This is exti0 as we spoke about before. So these are not there. They're all int default handlers like this. So generally when you are developing, you will not be in most cases you will not be having to write a startup file from the scratch. A startup file from another your past project or from some other maybe STM processor is going to be passed on to you, and you will have to modify that file and put in your changes. That's how it generally happens. You really don't need to write anything from the scratch, and even if you have to, you will have a lot of references. So assuming that SysTick handler is not here, you have int default handler. Okay, so this is not there. So how do you know? First of all, generally what happens is when you get such a startup file, by convention it is generally well commented, and you will find all the whatever interrupts are there, you will have it all commented. So it is not difficult for you to find out which interrupt you have to write the function pointer for. But just in case you really don't have it, you don't know which is where, then the reference manual is your best friend. You have to go to the interrupts and events, and then you have to get into this part. That is where your interrupt vector table for this particular processor is, and this is going to vary from SoC to SoC, as you know, right? So this particular processor's interrupt vector table is here. So we have the first is the stack pointer address, then you have the reset. Okay, but one thing again, up to SysTick it's universal right across all Cortex M processors, so you don't need to worry. It is only when you come to the EXTI we'll see that this could move around. So anyway, so we see that the SysTick is in the 6th position here. Sorry, SysTick is in the not in the 6th position. The number is 6. Okay, but let us see what is the position here. Okay, so we see that the first one is reserved, then you have reset. Let us open our startup file and let's try to compare what we see here. Okay, so once we compare, we will know that we will know where we are. So this is the first location, that is this one, that is your stack pointer, which is the reserved one. Okay, see this. Now later on we will be talking about this. This looks weird, this looks like a function pointer. That is because it has to be typecast to a function pointer, but it is actually an address. It's an address of the beginning of not the beginning, it's an address of the end of the array, because we know that you have to have the stack. Since it's a descending stack, you'll have to have the big starting address of the stack, and then you have to add the size of the stack, and that is what is put here. So we know that we have talked about it in great length. Then you have the reset ISR. So see, you have the reset ISR here. So this is the first reset interrupt. Then you have the NMI. So this is the NMI ISR. Okay, so see how this is going. Then you have the hard fault. So this is the fault ISR, hard fault handler. The name might vary, but then you have the mem manage bus fault and usage fault. So mem manage bus fault and usage fault are just not there. If it happens, it goes into the default handler. So default handler, you don't worry about that. And all zeros that are put here is for this reserved region. Four words are for the reserved region. Okay, so this part is reserved, so we have all zeros. So see how it is following the map that you have on in your reference manual. Okay. Yeah, this is very important. When you are working on a new controller, this is something that you have to be aware of. Then SV call is here, this one. Then you have debug monitor here. Okay, so this is all going into default because you are really not interested about these interrupts right now. Then SysTick SV call, debug monitor, and then you have a reserved region, which is this. See, reserved region, and then you have pend SV, which is again not used. And then comes the SysTick handler. So if the SysTick handler was not put in here, this is where you need to put the SysTick handler. Now this is SysTick handler. This name has to be the name of that function. Whatever SysTick handler function that you are writing, that is a SysTick handler function here. Whatever SysTick handler function you wrote has to be the same as this. So see, this SysTick handler here. If it had a different name, then that name is going to come here in the startup. That name has to be here. So the first step to take is write the name of the handler here. That's the function name. And you have to absolutely declare the function in a header file. You could declare it in the same startup GCC, but that's not a practice that I follow. I declare it in some other file and I just refer to it. So see how it is declared here. So this is the memory map. Sorry, this is where I declare it. So this is the core initialization. This is the core initialization file for where I have all the code, right? This is the respective header file. So this is the core initialization header file. I have, of course, all header files need to have an include guard. So that's almost mandatory. Otherwise, your code is going to be messed up. And then I'm declaring all the functions that is there in the core initialization here. So all the functions are declared here. So this SysTick handler is declared in the header file. The function is declared in the header file. If you don't declare the function in the header file, you'll see that it throws an error. It clearly does not work. In other places in the code, if you do not declare a function, probably it'll let you go with a warning. But if you do not declare the SysTick handler, let's try doing that. Okay, let's comment this out. So it's not declared. Okay. So the SysTick handler is not declared. The address is located. It mentioned in startup GCC. Okay, that is the function name, and I have not declared it here. Okay, so this is the situation. Suppose you commit a mistake and you forget to declare the SysTick handler here in the header file. Let's compile it and see what happens. Project, and I do a build all. Let's see what it says. See, failed 2 errors, 0 warnings. So what it says is, let's see the error. SysTick handler. So error, SysTick handler undeclared, not a function here. It checks up in startup gcc.c and it just gives you an error. Okay, so be careful whenever you are declaring a handler, whenever you are naming a handler in the startup vector interrupt vector table, the function has to be declared. Okay, so now if you build the project, you'll see it is built peacefully. But I'll show you one more interesting thing. Suppose I comment this out. That is a PLL init. As a PLL init is a function which is used for initializing the PLL. Okay. Suppose I just comment out the declaration of that particular function. Now that is not any function within the SysTick handler. Okay. Sorry, that's not any function within the startup. It is of course a function, but I am just not declaring it. And let's try to build the project and see what happens now. You'll see that it builds and gives you a warning. Okay, it may build and give you a warning, or it just may peacefully build. See, I have not even, this is completely commented out, but it's not throwing any warning. Okay, it generally gives you a warning. So let's comment out something else and check if we are seeing the, so let's do initialize or blink enable LEDs. So let's see, enable LEDs commented out. Okay, not declared. Project, let's do a clean, and let's do a build all. So we see we get one warning here. So what is the warning? Implicit declaration of enable LEDs. Okay, so you will get such warnings if you don't declare, but it will not stop you from running the code. Okay, but in the case of if you do not declare the SysTick handler or any handler that you have mentioned in, so this is another handler which we are going to see afterwards, but nevertheless, let's have a look at what happens. So int_i0 handler, which is this handler. Okay, check this out, this handler. Okay, so I've forgotten to declare that, suppose, and then let's just clean and build, let's build the project. Let's see what happens. See this, 2 errors, 0 warnings. So don't forget to look at this. So it will error out. So this is very strict as far as declaring the functions that you declare that you have in the interrupt vector table is concerned. So now it's going to build. So don't be alarmed if that happens. So the behavior is different. In one case, it still builds with warnings, but interrupt vector table, it will not forgive you. It's just going to throw an error. So now you put the SysTick handler function pointer into the interrupt vector table. Okay, so this is the first step that you have taken.